Have you ever wondered how we even know about the stars? They're so far away that we can't visit them, and we also can't even send instruments to measure things. How do we know their composition and their temperature? How do we know that they're moving away from us? Most of that information comes from one thing: light. The study of light is called spectroscopy. So what is light anyway? Light is a type of energy. It's a form of energy that can travel through space called electromagnetic radiation. And it's called that because the energy travels in the form of magnetic and electric waves. And traveling through space is key because space is a vacuum. There's no air. And not much can travel through space, but electromagnetic radiation can. This radiation has lots of different wavelengths. The one you're probably familiar with is visible light. Let's look at the whole spectrum of electromagnetic radiation. It goes from short wavelengths down here to long wavelengths over here. Now this is 10 to the minus 12. What can we compare to that? The nucleus of an atom is about that size. Pretty small, and we definitely cannot see it with a microscope. We move on to radiation that's 10 to the minus 10, 10 to the minus 8 meters. All of these things are very, very tiny, the size of atoms or maybe molecules, and we can't see them with visible light. On the other end of the spectrum, we have things that have much larger wavelengths, and the wavelength is the length of one wave. So from crest to crest, or trough to trough, it is the entire length of one wave. Out here we have electromagnetic radiation that's 100 meters in wavelength. So let's look at these different types of radiation. It turns out that the shorter the wavelength, the higher the energy, and the longer the wavelength, the lower the energy. So gamma rays down here at this end have extremely high energy, and they're very dangerous to life. Gamma rays are generally produced from radioactive decay, and if you're exposed to gamma rays, it's kind of like they go in and scramble your cells like an egg beater, and that's it, you're done for. X-rays are a little bit less energetic, a little less damaging, but when you go to the dentist and get your teeth x-rayed, the dental hygienist will put a lead shield on your chest so that you don't get x-rays to your vital organs, and then they'll run behind a wall and push the button, right? Well, that's because they don't want to be exposed to x-rays several times a day throughout their entire career. That wall actually has lead shielding in it. So it's fine to get x-rays once in a while, but not every day. Ultraviolet light is also damaging. It's the type of radiation that produces suntans, or what I call upcoming skin cancer. Then we have the visible wavelengths. Notice that the blue color is a bit shorter in wavelength than the red color. After that, we have infrared radiation, which is similar to heat, microwave radiation, and radio radiation. There's very little damage that can come from radio waves. In fact, they're passing through us right now. We can take a transistor radio and dial it in and pick up the radio. So remember, long wavelength, low energy, short wavelength, high energy. All of these travel at the speed of light, 300,000 kilometers a second or 186,000 miles per second. White light is made of all different colors, and if you pass white light through a prism, because the light bends or refracts inside the glass, it splits the colors into an arrangement like a fan. Each color bends a slightly different amount because the wavelength is slightly different. Red bends the least, and blue or violet bends the most. If you're a Pink Floyd fan, they got it backwards on their album. So how do we use this to tell us about stars? When stars emit light, they don't emit the entire rainbow spectrum. They only emit a couple different wavelengths because of the gases that they're made of. We have bright or dark line spectra at specific wavelengths that are produced by the composition of the source. Is the star made of hydrogen or helium or sodium? And then it produces these spectral lines. And they're kind of like a fingerprint for various elements. Imagine we had a hydrogen gas that was hot and glowing. That gas passes its light through a prism, and we see that it creates a series of lines, not a solid rainbow, but spectral lines that are indicating different energy levels that are excited in the atoms of hydrogen. We could try this for a different gas like neon. And in that case, we get a different pattern of spectral lines. So that's what I mean by a fingerprint. Every element has its own unique pattern of spectral lines. So how does this tell us about star composition? Well, there are three types of spectra. The first one is a continuous spectrum, and this is what we were looking at earlier. An incandescent light bulb produces white light with all colors in it. We pass it through a slit for various reasons and a prism, and we get the entire continuous spectrum, or the rainbow. However, if we do what I was just describing and we have the light come from a hot glowing gas instead, then we get a pattern called an emission line spectra, or a bright light spectra. And what's going on is that the gas is emitting energy at each of these wavelengths. And so that's what we see when we examine them. This can tell us about the composition of the star. The next type of spectra that I'm going to show you is sort of a mirror image of this. Instead of having bright spectral lines, we're going to have dark absorption lines. And this is when we have an incandescent light or a white light source pass through that gas, but the gas is not giving off its own energy. And in this case, it's going to absorb the various wavelengths and not let them pass through. And so we get a continuous spectrum from the white light, missing all the wavelengths that relate to the gas. And so in this way, we can look at stars and figure out what they're made of. Here's the spectrum for hydrogen. We have the emission line and absorption line spectra. And what you'll see is that there's a mirror image here of those different wavelengths. Now it turns out that hydrogen is a big emitter of red light. And so when we see something like the Orion Nebula, which actually has a red color, it's because of the heated hydrogen gas. Here's the sun's absorption line spectra. And this is now a combination of several different elements. We've got lines for hydrogen, but we also have spectral lines for calcium, iron, and sodium. So astronomers have to figure out, when they see all of these mixed together, what the signal is, what the elements are that are making up the star. A second thing that we can tell from light is the temperature of a star. Every object emits some sort of electromagnetic radiation, and that depends on the temperature of the object. So humans, for example, which are at 98.6 degrees, emit infrared wavelengths. That's what's shown here. And those would fall on this diagram here where I have wavelength, infrared, visible, and ultraviolet against intensity, right about here. The Earth overall is about 60 degrees Fahrenheit. It's a little bit farther along towards the infrared. If we look at the stars, we'll see how color really tells us a lot of information. Here's a red star that's at about 300 degrees Kelvin, which is similar to 300 degrees centigrade for our purposes. And the peak wavelength is in the region of red. So this is a red star. The sun, which is a yellow star and 6,000 degrees Kelvin, has a peak wavelength around the yellow. An even hotter star called Rigel has a 12,000 degree temperature, and that corresponds to a peak wavelength in the blue region over here. So as it says to the left, hotter objects radiate more energy at shorter wavelengths, which is higher energy. A third thing we can figure out is how stars are moving. And I'm going to make an analogy with something called the Doppler effect. You may have heard this before. If you hear an ambulance or a car approaching and it passes you, you'll notice that the sound of the siren or the car changes. As it approaches, it sounds rather high-pitched, and as it goes by, it sounds low-pitched. Here's my example. Right, like a race car. And the thing is, the sound isn't changing. If you were in that car, you wouldn't hear any change. But it's because that object is moving relative to the listener. So here's an ambulance, and it's moving away from this person. And because of that, the sound waves are being stretched. And sound waves that are further apart create a lower pitch. Over here, that ambulance is approaching this person, so the sound waves are bunched up. And sound waves that have a shorter wavelength are a higher pitch. So the same thing happens with light. If a star is moving towards us really fast, then the wavelengths are pushed together and they go into a shorter wavelength direction, which is blue. If the star is moving away from us really fast, the wavelengths are stretched and things are shifted towards the red. This is called a redshift. So here's an example of how this happens if we have a signal of sodium. Here's a standard spectral line for sodium. And down here, these sodium lines have been pushed to the red. They've been red shifted. And that tells us that the source, the star that's emitting these sodium lines, is moving away from us. On the other hand, if we have lines blue shifted, so these lines are further into the blue than here, then the source is moving towards us. Let's see if you figure that out. So in summary, light coming from stars can tell us quite a bit. The absorption line spectra can tell us the star's composition. What gases is it made of? The color of the star, the peak wavelength that it emits, tells us the temperature. And then we can see if the light is red shifted or blue shifted to tell us whether or not the object is moving towards us or away from us. Coming up next, stars.